Hi. So the topic of this lecture is radiation. Let's see, in brief, radiation occurs because when an object gets hot, its atoms vibrate, and those atoms have positive and negative charges in them, protons and electrons. And anytime we've got a vibrating charge, that vibrating charge will give off electromagnetic radiation. So radiation is actually electromagnetic radiation or electromagnetic waves that are propagating through vacuum or through air or really through all kinds of different mediums. So radiation occurs because we get a hot object, and that hot object gives off these electromagnetic waves depending on, well, how hot it is. Objects can have varying degrees of efficiency at how good they are at either giving off these electromagnetic waves or absorbing these electromagnetic waves. We've all experienced this. If you think about getting out of maybe a pool in the summertime, and you step onto the surface of the ground after getting out of the pool, they probably nice concrete around the pool, nice, kind of light colored. And then maybe you're heading to your car, or you're heading to your parents' car. There's some asphalt, some black asphalt that's on the other side of that concrete. And, while the concrete feels a little bit hot, possibly to your feet, bare feet, at the moment you step onto that asphalt, you have a completely different experience, right? That asphalt is extremely hot in the summertime. Why? Because the asphalt is a much better absorber than the concrete is. Because of the fact that the asphalt is a darker color, it is a better absorber. It also emits heat at a more efficient rate than concrete does. If we've got an object that is a perfect absorber, it's also a perfect emitter. That object is called a perfect black body. All right. So we can come up with an equation to describe heat transfer via radiation. So it's this one right here. Remember that Q there is heat. And it says that, well, our heat Q is equal to emissivity E times this Stefan-Boltzmann's constant times the temperature of our object raised to the fourth power. And note there that temperature has got to be in Kelvin, not Celsius, Kelvin, times the surface area of our object, times the amount of time that we're concerned about, that our object has to emit. Just to backtrack a little bit, electromagnetic radiation, electromagnetic waves, you might know this as light. Typically when I say the word light, we think of light as being visible light. But really we can have infrared light, we can have ultraviolet light, X-rays are light, microwaves are light. Just that whole broad electromagnetic spectrum is light. Okay. All right, so back to this equation here. This emissivity E is a measure of how efficient a emitter or absorber or object is. This emissivity E doesn't have a unit. It's got no units. It's always between 0 and 1. And if we've got a perfect black body, that perfect black body has an emissivity of 1. All right. Let's see what we can do with this. All right, so we've got here the star Betelgeuse. It says Betelgeuse has a surface temperature of 2900 Kelvin. And it says it emits a power of approximately 4 times 10 to the 30 watts. We're assuming that this star is spherical. We want to find its radius. And it says here that this star is a perfect emitter. So that tells me there that my emissivity is 1. And we want to find its radius. It's a sphere. A sphere has a surface area that's equal to 4 pi r squared. Okay. All right, the other thing we're given here is the power. This right here, it says power is 4 times 10 to the 30 watts. Now that equation that we had did not have power in it. It had heat, Q. It had temperature, T. But remember that heat is just a form of energy. If we think back to maybe a couple chapters ago, maybe Physics 1, we might remember that energy divided by time is power. So this number that we're given there is the power, and that power is Q over T. Okay. All right, so let's write out our equation. Q is equal to E sigma A T to the 4th times time. Let's divide both sides of that equation by time. That'll give us Q over T is equal to E sigma A T to the 4th times T. And that Q over T, what is that Q over the T? That Q over T is just power. So let's just get rid of that and let's just put power in its place. This is power. All right. And now if we want to solve for our radius there, it looks like what do we need to do? We need to isolate area. So if I divide everything by the multipliers of area, I will end up getting an expression for area. It looks like area is equal to power over E sigma T to the 4th. Boom. And as a matter of fact, that T right there is not supposed to be there because we divided what Q by T so that to get power, so that T should have been gone. Yeah. There we go. Okay, at this point, I can go ahead and put in some numbers. So our power is 4 times 10 to the 30 watts. E is 1. Sigma is 5.67 times 10 to the negative 8. Let's see, watts dot meter squared per Kelvin to the 4th. And then our temperature is 2900 Kelvin. All right. And so when I put all that into a calculator, I get out that my surface area is, let's see, what is it? 9.97 times 10 to the 23 square meters. All right, so that's the surface area there. That's great, but we wanted what? We wanted the radius. Okay. So let's get that real quick. Give myself a little space here. There we go. Let's see here, and let's grab a different color. Maybe let's grab green. All right, so area is 4 pi. Whoops, my bad. Where'd we go? Okay. One more time. Area is 4 pi r squared. That means that, let's see, if I solve this guy for r, I'm going to get r squared is equal to area divided by 4 pi. If I take the root of both sides, I get r is equal to the root of area divided by 4 pi. And now I can plug that number in there for area, my 9.97 times 10 to the 23, divide by 4 pi and take the root. And I will get that the radius of this star is 2.8 times 10 to the 11 meters. And that is the result for this particular problem. All right, so let's move on. Let's try something else here. It says what? We've got a person. Total surface area of this particular person is 1.7 square meters. So all of the skin of the person, the outside area of the person is 1.7 square meters. We're going to assume a person has an emissivity of 0.97. That number is a little bit unrealistic. It's probably more in the range of 0.73, 0.75, something like this. But nevertheless, that's the number that I've chalked up on the problem. So we'll work with that. Let's see. It says what? Find the net energy lost by a person via radiation in a room held at a temperature of 64 degrees Fahrenheit over an 8-hour period. All right. So this person, let's see, 8-hour period. Maybe they're asleep, I guess, in their bed. The room temperature is 64 degrees. We want to find the net energy lost by this person. Person's at a temperature of 37 degrees Celsius, room's at 18 degrees Celsius. Okay. So the first thing we want to do is we want to try to take care of these temperatures here. The temperature of the person, because we cannot operate in Celsius. We've got to operate in Kelvin. So 37 degrees Celsius is 310 Kelvin. All right, and then the temperature of the room, what is this? 18 degrees Celsius plus 273. Sorry about the streaks. These things happen sometimes because of my my screen, I think. And that gives us the temperature of the room there is 291 Kelvin. $291 Kelvin. I'm just going to leave that there. All right. So there we go. So we've got that. Now, this problem asks about the net energy. So as this person is in this room, not only is the person giving off energy because of the person's body temperature, the person is also absorbing energy from their surroundings because of the temperature of their surroundings. So they're emitting energy through their skin. They're also absorbing energy through their skin. Okay. So our Q net, our net energy, is going to be equal to the energy emitted by the person minus the energy absorbed. All right. So let's see if we can write this out further. We've got that equation for Q. Q net here is going to be equal to what? The emissivity of the person times sigma, that's just a constant, times the area of my person times the temperature of the person raised to the 4th power times the time. Okay, so that's the heat that the person is emitting. What about the heat that the person is absorbing? Well, again, we've got that emissivity of the person times that Stefan Boltzmann's constant times the area of the person, because the person has this amount of area to absorb heat through. And then let's see, what is the temperature of the person's surroundings that they're surrounding heat from? That's the temperature of the room raised to the 4th power times time. So if you notice here, in these two expressions, everything is the same except for the temperatures. So what I'm going to do is I'm going to factor out everything from both terms except for the temperatures. And that'll give me something that's a little bit easier to work with. E sigma A person times time. And then what do we have left? We've got the temperature of the person raised to the 4th power minus the temperature of the room raised to the 4th power. There we go. And at this point, we can just go ahead and plug in numbers. Well, let's see. Is there anything we should do first? It looks like maybe we do need to take care of one thing. The time there's 8 hours. Of course, we don't operate in hours, do we? No, we need to operate in what? In seconds. So 8 hours is 28,800 seconds. How do I know that? Well, there's 3,600 seconds in an hour. So I just multiply that 8 hours by 3,600. Okay. And now I can go ahead and plug in numbers here. Okay. The emissivity of a person is 0.97. Let's see here if I can get my, there we go. Sigma is 5.67. Surface area is 1.7 square meters. The time is 28,800 seconds. Whew, that's a lot. And then I've still got this, this bit here, my temperatures right there. So let's see, all of this that I've written out times what? Times the temperature of the person. It's 310 Kelvin raised to the 4th power, minus the temperature of the room. That's 291 Kelvin raised to the 4th power. There we go. And we'll see how much heat that is real quick. So let's see, it looks like I've run out of space a little bit. Let me just do this. Let's go up here. All right, so when I perform that calculation down there at the bottom, I got a net heat of 3.27 times 10 to the 6th joules. There we go. Okay, let's see. So that is my answer for the amount of heat that a person loses in 8 hours if they're in a room at 18 degrees Celsius. Okay. A couple things here real quick, or at least one thing here real quick. We notice here, circled in red, this expression is t to the 4th minus t to the 4th. Okay, and it's got to be that way. This is a common mistake that I've certainly seen in the past. Is I have seen people do, instead of t to the 4th minus t to the 4th, they've done something like this. They've done what? Temperature of person minus temperature of room raised to the 4th power. Now that is a much different number than the one that's circled in red there, the t person to the 4th minus t room to the 4th. So these are not mathematically equivalent. This right here is just wrong. So please be sure not to do that. All right. So great. So the amount of heat that this person loses is 3.27 times 10 to the 6 joules. Typically, if we think about people in energy, we think about energy in terms of food calories. Food calories are what's called kilocalories. But yeah, let's just operate off food calories. So 3.27 times 10 to the 6 joules. Great. If we've got 3.27 times 10 to the 6 joules, my question is, well, how many food calories is that? Because food calories is a unit of energy, joules is a unit of energy. So let's just convert that. And you can see here that I've got a conversion factor. So let's do that. So in order to use this conversion factor, what do? I multiply by the correct ratio, 2.39 times 10 to the 4th food calories for every 1 joule. Why do I do it that way? Because if I do it that way, I can get rather nicely, see I've got joules there, I'm dividing by joules there, those units cancel out, and I end up with units of food calories. All right, so when I carry through this multiplication, I get the result that this ends up being 1,330 food calories. That's a lot, actually. You think about the amount of calories that we're told we're supposed to take in a day, depending on it depends on, of course, what sex. It depends on activity level, so on and so forth. But on average, 2,000 calories, 2,500 calories, depending on what our our individual needs are. But so burning up 1,330 food calories is a lot. Let's see. Let's say that instead of having our room at 64 degrees Fahrenheit, we had our room at 72 degrees Fahrenheit. In that case, we would end up with 1,060 food calories burned up. What's, okay, we do lose some energy, certainly, from maintaining our body temperature when we're in surroundings that are different than our body temperature, but not quite this much. So my question here is, what's wrong with this analysis that we've done? And you might be screaming at me that the first thing is the emissivity that we used, and I would agree with you that emissivity is a bit too high. Nevertheless, there's an additional problem here. And that additional problem is that when we sleep, we tend to have some covers, some blankets, so on and so forth. So we've got some layers of insulation around ourselves that trap heat. We still certainly will lose energy. Absolutely. We will burn food calories by being in a cool room. And the cooler the room is, the more food calories you're going to burn. If you sleep with, which most of us do, sleep with sheets, blankets, so on and so forth, it's going to decrease the rate of that energy burn. So this has actually been studied. Having people sleep in different room temperatures, and there's a link at the bottom of this page. Of course, it's kind of hard to click on a link on YouTube, but nevertheless, you can do a little Google search on this. This has actually been studied about a decade ago now, is the one that I've got in mind. And it was actually found that, yes, by decreasing the temperature of the room that you sleep in, you actually can lose a little bit of weight. Not a ton, but a little bit of weight. They had a control group and a trial group, and yeah, they definitely found a difference there between those two groups. So, all right. That does it for this particular video.